Okay, good evening to everyone. My name is Anandan Susai. I'm doing PhD in engineering under supervision of Dr. Sivakumar Sivanesan. Okay, my research title is about mechanical properties and low temperature degradation behavior of alumina zirconia ceramic composite. So this is my outline. So first, let's go through about the research background. So my research is about something to do with the ceramic which is used in biomedical application. So first, we know that hip transplant is the most well-known surgical procedure in orthopedic field around the world. It estimated about 500,000 of patients was found in US in each year, and it's growing. At the beginning, the type of metal used to replace the hip ball is by metal fused. They use a metal fused to the bone by a cement and socket made of polyethylene was implemented. But this technique has a major disadvantage. The disadvantage has been found that it has a very short duration of lifetime. That means it's prone to get failure within 12 years. So those who used this metal as a hip replacement, they need to replace it after 12 years. So that's a big issue about this technique. Then in 1990s, another substance called yttria stabilized zirconia was introduced. Zirconia is a type of ceramic. So what added with yttria, and it has a certain advantage using this compared to the earlier material. The advantage is found to be it has a very high fracture toughness and better mechanical strength. It's a better mechanical strength. So means what? It not very easily breaks, and high fracture toughness. High fracture toughness means if any fracture happens, the rate of growth of the fracture will be small. Okay, it will be small, so it won't damage the overall structure. So high fracture toughness compared to the earlier material. But although it has this very good advantage, but it has another one disadvantage. This material is it has disadvantage is it's very sensitive to the low temperature degradation. So when you go to the low temperature, what happened? The zirconia grain size start to grow, and when it grows, the zirconia material, the yttria stabilized zirconia, the surface become more rough and causes failure. Okay, so when go to the low temperature degradation, it become more rough and loses its mechanical strength. The mechanical strength get weaker when the grain size get larger. So this the structure shows that this the hip ball made of zirconia. So then concurrently another material was used alternative to the zirconia. It was called alumina zirconia composite. Alumina zirconia was together add as a composite, was proposed in biomedical application to overcome the low temperature degradation faced by the zirconia. So alumina zirconia advantage is it's very good in hydrothermal stability, very good hydrothermal stability, less sensitive to the low temperature degradation. That means not easily become rough. The grain size not really grows fast as zirconia, yttria zirconia. Low temperature is less sensitive to the low temperature degradation, so not prone to failure. But it also has a disadvantage. The disadvantage is the mechanical strength of the zirconia alumina zirconia composite is found to be 700 to 1000 megapascal, which is average. Like E3 zirconia is able to achieve up to 2200 megapascal, so quite good mechanical strength. So alumina, although low temperature degradation is good, but poor, not say poor, average mechanical strength. So it can easily break relative to the E3 zirconia. So the factor determines the mechanical strength. Of course, the grain size. How big is the grain size? Much more smaller the grain size, the most probably it will be in form of tetragonal phase, a very stable phase. So therefore, research found to be more in tetragonal phase means more higher mechanical strength it has. So smaller microstructure, better mechanical strength. And second, what determines the mechanical strength is the technique used to development of the composite. Okay, like what are the techniques they use to minimize the size of the grain. So problem statement for my research is further research is required for the composite elaboration of alumina zirconia in terms of powder mixing technique, uh, in terms of dispersion, how well the zirconia has been dispersed on the alumina surface, and atomization, pressing and sintering required to improve homogeneity of the microstructure in powder mixing, to increase the flexural strength up to 1200 megapascal and grain size below 500 nanometer. So my research objective is to develop a ZTA composite system optimum volume percentage of alumina and zirconia content that complies with the industrial standard ISO 6474 to 2019. Another objective is to introduce a more innovative and simple and cheaper method to obtain a ZTA composite without compromising the mechanical properties and acceptable low temperature degradation. And third, to develop a ZTA composite which is capable to withstand a high low temperature degradation for biomedical applications. So research method. Now the technique we're going to use to develop the ZTA is the ZTA composite to be developed through a colloidal method. Okay, compared to the normal powder processing, we use a colloidal method with an optimum volume percentage of alumina zirconia to be found that could exhibit optimum mechanical properties and acceptable hydrothermal stability. So in the development of the green body, first we use the available alumina powder was used to modify to prepare the composite powder. The powder must undergo a critical analysis such as the resistance against temperature, effect of each experimental process and phase transformation to be checked carefully. The degree of homogeneity of zirconia grain dispersion of the alumina matrix will be analyzed. Okay, first, the powder elaboration. Alumina powder commercially available from Japan will be used to prepare the ZTA composite powder for investigation. The alumina powder will be dispersed in water for a duration of 3 hours by incorporating with alumina sphere. Then zirconium chloride aqueous will be added in a suitable volume. The drying process will be initiated by using a drying machine with a 2 fluid nozzle. So break them into a small tiny powder. Okay, so we use the drying process. Then the important process in colloidal method is the sleep casting. A liquid clay body sleep is poured into a porous mold, produce a layer on the inside walls, the wall after the significant time interval. The powder obtained from the isostatic pressing sleep casting will be sintered, a type of process which is used to densify the substance by using electrical furnace. After that, hot isostatic pressure about 520 degrees Celsius at a rate of 10 degrees Celsius per minute will be used. to further densify the green body. Then this is the flow chart of the process. Then finally, it's ready for the mechanical properties evaluation of the structural evaluation, such as what do you call fracture toughness, Young modulus, and everything. So in a preliminary work now, currently I've did preliminary testing by using conducting a composite with 92.2 to 99.8 zirconia content, and the finding were also published in Material Science Forum. The paper has been published, and hardness of the composite has been discovered for a different amount of zirconia, and the toughness also has been investigated and found to be the value of the toughness and hardness has been improved about quite significantly compared to the normal powder preparation. And the grain size found to be significantly able to reduce up to close to 500 nanometer. So through this research, the powder preparation by using colloidal method can be proved to be innovative, simple, and cheaper. The composite powder without compromising the mechanical properties and the hydrothermal stability can be achieved. This research is aligned to the National Key Economic Area under Health and Entry Point Project Medical Devices. This research is also supported by the United Nations Sustainable Development Goal by contributing to the Goal 3, good health and well-being. Okay, thank you. That's all my presentation about my research. Thanks.